Probably no.
Okay, so let's have a little talk here. We're gonna do our introduction to a topic that's I think apropos, Eastern Oregon, Pendleton. We might call this. We might call this. In fact, let's go ahead and label this talk.
I mean, you're not wrong.
What are we doing?
Buying trucks.
Heck yeah.
Oh man, I don't like trucks.
I
You gotta have
don't-
like beer and
Guns.
tractors.
The
guns.
truck has to come first.
Could be other
America.
stuff too, but we're just gonna call this is buying
Oil.
buying trucks. Okay,
Buying
so
trucks.
buying trucks. Let's take a little example. Anybody got a beater, little 4-cylinder truck in here?
Me.
Do you?
My neighbor
Well,
does.
it's like a
Did.
Nova, I don't know.
Well, what do you got?
It's gotta be
We have
Nova.
like a Toyota from 1980.
Okay, so it is an old 4-cylinder truck. Okay.
My neighbor had
An
a
87 Nova.
Does anybody have like a huge diesel turbo powered?
Probably it's a Dodge.
Okay, so you got a big Dodge diesel truck also. Okay. So let's say
both
we
ends of the
got
spectrum.
we have scenario A and scenario B. Scenario A is that Lily's family in their big supercharged Dodge diesel truck is going to pull a large trailer with with horses. Total mass of, let's say, it's big, 5,000 kilograms. So we're over 10,000 pounds. Okay.
It had
Up.
1 horsepower. This one.
Up Cabbage Hill. Yeah, up Cabbage Hill. Going 80 miles an hour in 5th gear, zooming up the whole way. Starts at the bottom, gets to the top. Let's just say, I'm just making this up, but let's just say that they're gonna go all the way up to like Dead Man's Pass, and let's just say hypothetically that they're gonna gain 1,000 meters in elevation. Probably not quite that much, but let's just say they are. Okay, going up the road. They do that at 80 miles an hour. I mean, it's just not even slowing down, right? Okay, next time, they're gonna hook up that same trailer with a little 1984
Yeah.
Toyota
Yeah.
4-cylinder pickup, and they're gonna pull it up to the top also.
At 80 miles an hour.
No.
I
This
didn't- I
time,
couldn't reach
this
80 miles
time
an
they're
hour.
gonna put it in 1st gear, and they're gonna run it up to the top at an average speed of about 5 miles an hour. Okay, which it probably could do, right, if it's in 1st gear. Which truck does more work?
They both do the same.
They both do the same amount of work, that's true.
Well, to the trailer.
They both do the same amount of work on the trailer.
Yeah,
right?
because the
Okay.
size of the trucks would make it.
That's true. But let's just say the amount of work on the trailer, right? They both do the same amount of work. That's true. They both apply the same amount of force through the same distance, right? And really, all they need, if we want to calculate the work they do, we could just take the weight of the trailer times what? The length of the road?
That was the height of the.
The change in elevation, right? Good, because that's the line of force is vertical. So all we care about is the vertical part of the displacement, right? Something's different though. What's different?
The time it takes.
The energy, actually, they both, probably one car's more efficient than the other, but aside from that, the work that they've done is all done to do what? To change the kinetic, well, I mean, let's assume that they start from rest and they end from rest at the top. All they did was, the energy that they invested was the potential energy that they end up with, right? The change in potential energy. So even that's the same. Something's different though.
The rate at which they
Oh,
do the work.
the rate at which they're doing the work is very different, right? Very different. So that must be something important. What do you think you call that in physics? Any guesses? So you're gonna fill in the blanks. Something equals
Something.
work over time. Well, so what's it again? Heard somebody say something.
I said watts.
You said watts?
Yeah.
Watts is the unit of this.
What?
Yeah. It's the unit of this thing.
So it's changing,
I
so
guess.
it's basically changing energy over time, right?
It's, well, I mean, yeah, but it's defined as work divided by time. So it's the rate at which work is the real definition of this. It is power. That's it, it's power. So power P is equal to the rate of change at which we do work. So what are the units gonna be? What are the units of work?
Joules per second.
Joules, and time we measure in seconds, yeah. So the unit of power is a joule per second, which is, it's what? So what, yeah, so that's the SI unit. Now, there are other units too. I mean, what's the unit that, if you were buying trucks, what was the
Horsepower.
unit? Yeah, it'd be horsepower, right? Horsepower is kind of, it's a dumb one, but that's the one that we use for cars. And so when you buy a car that has a lot of power, right, if you buy a car with massive horsepower, what's the advantage of that?
They can do work faster.
It can do work faster, yeah, it can do work faster. So if you take Nick, what's a car that has a tremendous amount of horsepower?
2009
Has, how many horsepower?
330.
How many?
330.
330. For that little car?
Yeah.
Wow, that's a lot. 330.
The
That means
Impala
that-
has about
okay.
that much.
So what does all that horsepower do? It's going
Turns
to,
the wheels.
It follows the law.
it's gonna follow the law, exactly. But it has the potential to go from point A to point B by accelerating very quickly and doing lots of work in a short amount of time. Now, we're gonna talk about some other quantities here soon. That there's another quantity that we typically refer to when we're buying trucks. And that has some impact on our decision as well. But really, this car, the reason that it has high horsepower is so it can go real fast and accelerate real fast, right? Let's take an object like, what if you wanted to push over a house? That wouldn't be a very good choice, right? What kind of piece of equipment would you probably go down and rent if you wanted to, you just rent a bulldozer, right? Diesel bulldozer. Okay, how many horsepower do you think a bulldozer has? 20, 40, something like that. That's it. Why so little?
That's high torque. Move time.
Okay, right, because it's the idea here is not to do lots of work in a short period of time. They're different. Bulldozers are designed to apply lots of force, but pretty slowly, right? So they really aren't very powerful. They're like a tank doesn't have very many horsepower, but tanks probably they can go pretty fast. But I mean, you know what I mean? It's the objects that want to push really hard. You don't necessarily need a lot of power, right? You're not so concerned about being able to push it over really fast. You just want to be able to push the walls over, right? Okay, so then let's think about this. Let's go ahead and make a calculation of what is the power of each of those, right? So let's say that we're going to move from the bottom to the top of the hill, and it's 1,000 meter change in elevation, right? So let's summarize all this stuff. And let's say we can do this in the truck. We could do this in 6 minutes. It's pretty fast.
Which truck?
The Dodge. Well, that'd be a challenge, but Dodge did it in 6 minutes. The Toyota can do it in 60 minutes. See if we can do a calculation here of the work output of each of those trucks. How much work is done? How are we going to calculate the work done by the Dodge? We said that the mass was 10,000. Oh no, if I said 5,000, didn't I? 5,000. That's the mass of the load. What's the mass of the truck? That Dodge truck?
Doesn't matter.
Well, let's go ahead and just calculate it. So let's figure out what the output of the engine is while we're at it. So the output of the engine's got to push the car too, right? What's that mass is going to be probably 3 tons, 4 tons? I don't know, what do you think? Big Dodge truck?
3 tons.
3 tons, we'll say. Okay, so the mass of the Dodge is, we'll say, if it's 3 tons, we'll say it's about, we'll go a little more than that. We'll say 6,000, no, 3, is it 3 tons? 3,000, what's that gonna be? 3 tons, 6,000 pounds, that's gonna be about,
On the
yeah, about
garbage.
3,000 kilograms, we'll say.
Yeah, that's about where it comes out the garbage.
That's about what it does, about 3,000, okay? Well, Lily's always got all the answers, that's pretty good. She's got the numbers. She had the grade for us that one time. That's pretty good. 3,000.
Truck weight. I do that too.
Have you ever taken a load in the Toyota?
No, because we just got that because my grandpa died.
Oh. So the mass of the Toyota, let's say that's about, well, that's not gonna be very much. Probably 1,500 kilograms. Probably not even that, we'll say 1,500. So what are we gonna do to calculate the work then? I mean, sorry, the power. There's 2 parts to it, really.
That's
Find the
acceleration.
work,
Okay, find the work,
and then find the power.
divide by the time, sure, okay. So what's the work? So for the Dodge, the work for the Dodge is gonna equal the force. Okay, so what's the force that's it's moving up the road in cruise control. So what's the force? We'll ignore all the other inefficiencies. Ignore friction, everything else. So what's it gonna be?
9.8.
Times,
Cosine theta.
5,000. Well, 8,000, okay?
Yeah.
So 9.8 times 8,000 is gonna be the force, right? Times
Times 1,000.
displacement, vertical displacement is gonna be 1,000 meters, right?
So divide by
Divided by 6 minutes is how many seconds?
260.
336, yeah.
Yeah.
360.
Yeah.
Okay. So what's that work have to be? Those are all standard units. So somebody with your fancy calculator. Is anybody missing a calculator?
Mm-mm.
Okay.
Oops, that's wrong word.
Yeah, I don't want my truck.
1,000.
Shut up, I know.
Whoa. 217,777.
217,000.
777.
Okay, so we'll just say it's about 218,000 watts or about 218 kilowatts. The output. Okay, that's a lot, right? Compare that to like a microwave is how many? 1,200 watts, something like that. So that's pretty big.
Yeah, like a light bulb.
I'm not trivial, but is the W for the unit supposed to be capitalized?
It is. It's always capitalized. Yep. It's always capitalized.
Did you say our microwave was 1,200 watts?
Microwave's about 1,200 watts, I think.
Yeah.
So that's
Yeah.
1.2 kilowatts.
Yeah. Yeah.
So 200 microwaves and you'd have,
Yeah.
that's really powerful for a microwave.
I don't think so.
It's got a
Yeah. Microwaves do. They do a lot.
Wait, so the power of 200 microwaves could get,
You get a trailer.
Yeah.
Well, it's
Yeah.
a different kind of energy.
Welcome to the
Yeah, it is. Different kind of.
Microwave powered cars.
I mean, it's electrical, but so if you think about, like, sometime we'll try to do another calculation like a train. If you think about, I mean, that's really not very much, right?
That seems like a decent amount.
I mean, it's a lot, but compare that to the amount of power that's being exerted by a locomotive or something, and it's staggeringly high, right?
Oh, yeah, that's a lot.
So I mean, it's quite a bit, but the diesel, I mean, like an internal combustion engine is really not very efficient, right? I mean, it's, a lot of there's a lot of heat released, it's really not very efficient, whereas a microwave is pretty efficient, right? I mean, it's,
I was thinking
Just start putting microwaves in cars.
what's that?
I was thinking of a toaster and you said microwave, but still, that's crazy.
Yeah.
Yeah, how much does
Well, I mean, a
use?
toaster's, I don't know, 600 watts or something probably, what do you think?
So it take
Yeah, it does toast your food.
half a million toasters.
But you're not thinking about
Does
is
have to
all
toast
the-
food.
So here's the way to maybe put that in perspective. Think about what it takes to generate that power. Like what if your power went out? You'd have to go out and start a generator, right? And what are those generators? What's a generator? Probably 600 watts, 1200. I mean, 1200 watts. I don't know. But one of those big generators, that's an internal combustion engine, right? Maybe really big ones are 10,000 watts or something. But I mean, so that makes sense, right? The car's it's a bigger engine than the generator, and so it's.
Start making huge.
Yeah. Okay, let's look at the Toyota. So the Toyota, it's almost the same calculation, isn't it? The work due to Toyota would be 9.8 times 4,500 times,
Yeah, 60.
6,500, whoops. Times 1,000 divided by 60. What's that?
694 watts.
That's really low.
60 minutes is how many?
Wait,
3,600,
Yeah.
right? Which is about, did you give me a number, Paul?
Yeah, 17,694 watts.
Okay, so we'll say it's about 18,000, it's a little less, but it's about 18
About 200,000
kilowatts.
watts. About 200 kilowatts less.
Yeah, it's a lot, right? It's a lot less. And what is probably, that probably works out to be about right, too. I mean, maybe that's a little extreme. 6 minutes that'd be pushing it a little bit. So that's probably a little high. But, think about what is, you suppose, you guys know more about cars than I do, but we think about like a big diesel truck's probably got 600 horsepower, something like that probably. And what's a little, we used to have a little Toyota pick, I bet the thing has about
It's just used
65 horsepower, maybe, right? So you're talking about a factor of 10, so we're off by a little bit, but, it's probably fairly close. Yeah. Yes, sir. Yeah, you can. Yeah, go ahead. Okay, so that's work. So let's try a problem here then. So I want you to, let's think about something different, a little different application. Okay, so let's think about, let's say this time that we've got some kind of a pulley wheel that's being driven by a motor, and we're gonna pick up an object vertically that has a mass of m, okay? And we're gonna pick it up through a distance of h at a certain, in a certain amount of time, okay? So let's say we're gonna move it up h in t seconds. So let's come up with an expression that gives us gives us power this time, right? So power is equal to work divided by time, right? What's the work here?
Force.
Okay, so that's going to be mgh, right? Everybody agree?
Yep.
Okay, divided by t, correct? Call it delta t, right? Let's call this delta h.
So power is just, another thing is everything over time, like what has all happened over time?
It's the work that's being done divided by the time required to do the work.
Pretty much it.
Okay, so we're gonna apply a force through a distance and then divide that by time that gives you power. Okay? We could reorganize this though, couldn't we? Right? We could reorganize this as mg times delta h over delta t. What's delta h over delta t in this case?
displacement over time.
Yeah, what does that sound like?
Velocity.
Yeah, it sounds like speed, doesn't it? That's the speed at which we're raising this thing, right? What is mg in general? That's the force we're applying, isn't it? Right? So we could make this even more general. We know that if power equals force times displacement, and we're dividing that whole thing by time, that's really just the same thing as force times speed, right? Okay, so if something is being, sometimes it's convenient, if you know the speed at which something is being moved, if you know the force that's being applied, that's a pretty easy way to calculate power. It's not the definition, but it's a convenient byproduct of the definition, right? Okay? All right, so we got power, and you guys will get some practice with that. Get the idea what power is, though. Let's look at, I'm just going to introduce a new topic here, something that's, let's take an example of a ramp. Okay, we're just going to we're going to explore some motion up and down a ramp here for a second. So if we've got this ramp, and at a certain angle, I want to give you the angle, but let's just say that, okay, let's say that the length of the ramp here, we're going to call that L, and the height of the ramp, we're going to call Y. Okay, and we've got this thing all greased up, so we're able to push or pull a mass, with slip ring, there you go, let's go to the slip ring. We're able to push a mass up this ramp. Okay, what's the work required to slide this thing up the ramp to this platform at the top? It has a mass of M.
Wait, what was the question?
What's the work required to slide this thing up the ramp?
MGY.
Yeah, just to move it, we're just going to move it along the ramp. I'll even give you a little bit, let's just go ahead and say that, we're going to call that F1 is the force that we're applying.
Cosine theta
Work
and
of
y.
friction plus work of,
Okay, but remember, it's coated with slip rim, so there's no friction.
just the work of going up.
Okay, so what is that? What would we say?
And
Yeah, well, I'll tell you, let's just call it F. We don't need to call it F sub 1. We'll keep, that's a little overkill. I just needed a Toyota and I haven't started with Dodge. So what do we get? What's our work to push it up the ramp? So, okay, but if I'm pushing it through that whole, I'm pushing it with a force F.
Just that.
So F
That's L.
Y.
times L, yeah, right? Force times displacement, right? So the force I'm applying here, in this case, the force I'm applying is parallel to the ramp, and it's got a magnitude of F, right? So the work that we're applying by pushing it up the ramp, we'll call that work to push, equals FL, okay? What's the work required instead? Well, what if we just took that same box and we just lifted it up directly to,
MGY.
what's that gonna be?
MGY.
Okay, so the work to lift would just be, now the force I'm applying is the weight mg. Everybody agree?
Yeah.
Mgy. Which one's bigger?
Are they gonna be the same?
How, prove it.
Because it's a conservative.
Okay, because there's no friction acting, and there's the best way to do it, because the only forces acting are conservative, right? We're working against gravity and there's no friction. So the work required to get this thing from there to there, absent friction, has to be the same, right? Because it's in a conservative, force field, right? Everybody agree? Okay, so they're the same. Well, how much force is applied if we push it up the ramp? Less, you're right, less. So if we calculate F, look what we get here. So we get FL equals mgy. If I solve for F is equal to mg, the weight of the object, times the ratio y over L, right? So the steeper the ramp, the less advantage you have, right? Does that make sense? Everybody with me?
Mm-hmm.
Okay? The steeper the ramp, the less advantage you have there. The shallower the ramp, the smaller this ratio is going to be, right? Okay? So there is potentially some advantage to this though, isn't there? Right? Picking this, if this is a really heavy box, if we had a long ramp, we could apply much less force and get the thing up to the top. What do you suppose we could call this ratio right here of y divided by L?
Angle.
Well, I mean, it is the tangent of the angle, that's true. But it's not the angle itself.
The tangent of the angle.
I mean, we could call it the tangent of theta if we wanted to, right? But what, it did give us an advantage, didn't it? So what do you think we might call that? You've heard this term
Leverage.
before. What?
Leverage.
It's like leverage.
Come on.
It gives us an advantage. And this is a mechanical entity.
Mechanical advantage.
It's mechanical advantage, yeah. Okay.
What?
So the ratio of the ratio of the height of the ramp to the length of the ramp tells us that's what we call the theoretical mechanical advantage. This is just a simple machine, it's an inclined plane, right? So what this does is it changes the profile of the work that you do, right? You're able to do the same amount of work with less force by pushing it up the ramp. What's the disadvantage?
It takes
to have a ramp.
It might take longer, but you gotta say it again. You don't have a ramp. Now what's
I
the?
was fixing to push it farther.
You gotta push it further. Yeah, you gotta you have to apply the force through a longer distance. But frequently, that's not the problem, is it? Like if you're moving across town or across the state, you're probably gonna go rent a U-Haul or something like that, right? When you rent a U-Haul, you probably better hope that it has what on the back? A ramp, yeah. If it doesn't have a ramp, you're gonna be in some trouble, aren't you? When you gotta put that piano in the back of the U-Haul, picking that thing up
It's more
directly,
professional to do that.
you probably do, right? But when you're picking up that heavy furniture, to put it in the back, I mean, that's, the impediment there is, it's really heavy, right? So what do? Well, we put it on a dolly and we roll it up the ramp because, we got lots of time. We don't care if we have to push it. I mean, that's no big deal to push it an extra, several meters to get it up into the back. We're willing to do that extra stuff if we can apply less force, right? Does that make sense?
Yeah.
So mechanical advantage, if mechanical advantage is like this, I mean, we end up with a useful mechanical advantage that multiplies our force. Actually, this is backwards. The mechanical advantage it's the reciprocal of that, but it tells you how much you're multiplying your force, right? So based on this argument, because we're applying less force, what we really should do if we want to calculate the theoretical mechanical advantage is we're going to calculate the ratio of the output force divided by the input force, right? So think of this as what is the machine actually accomplishing divided by what kind of force do we have to apply to the machine, right? So if I were to do that, I'm really just flipping this thing around, right? And that's just going to equal L, in our case, L over Y for our ramp that we drew, right? So if the ramp is twice as long as it is high, we get a mechanical advantage of 2. We only have to apply half as much force, okay? What do you suppose, that's theoretical mechanical advantage. Let's say we do this experiment, and let's put some numbers on this. So let's say that the value of the mass is 300 kilograms, and the height of the ramp is 2 meters, and the length of the ramp is 4 meters, okay? And we do all this stuff, and we find that, let's say, the force that we have to input ends up actually being about 2,000 newtons. Okay, what is the theoretical mechanical advantage in this case? 2, right? because the ramp is twice as long as it is high. So theoretically, what should the input force be?
1,000?
It should be, what is the weight of this thing? It's roughly 3,000 newtons. So it should be what? The input force should theoretically be half of the output force, which is the weight of the thing, right? Everybody see that? Then we talk about output force. What's the force that the machine is actually overcoming, right? It's lifting up vertically how much weight? Well, 3,000 kilograms times 9.8, roughly 10 meters per second squared would give us about 3,000 newtons, right? Think about it this way. What would we have to do absent the machine? The machine wasn't there. We got to pick up the 3,000 Newton object. So that's what it's accomplishing for us, right? But we didn't get that. Our input force in this case, so our input force should have been 1,500 newtons, theoretically, but it was actually that. How come?
Friction.
Because there was some friction in reality, wasn't there, right? Okay, so then what do you suppose the actual mechanical advantage was here?
That minus the frictional force?
The actual mechanical, in actuality, the input force wasn't what we
Is
thought
that
it
going to be
was.
the theoretical mechanical?
What was it, what do you think, Richard?
3/2.
3/2. Yeah, that's right. Because in actuality, the output force was 3,000 newtons and the input force was 2,000 newtons. So we end up with 1.5, right? So when we calculate the theoretical mechanical advantage, really, that formula isn't probably what we want, is it? Because that may or may not end up actually being the case. What would we base our theoretical mechanical advantage on?
Forces.
I mean, if we were just to look at the ramp, we don't know anything about the surfaces. Theoretically, perfect scenario, we bought a ramp or we built a ramp that's coated in slip ram. What would you predict the best mechanical advantage would be? What do you think? Cyrus, what do you think if this was a perfect ramp, no friction, what would it be?
Ramp.
Yeah, I mean, but what would the mechanical advantage be?
I'm not sure.
So it's not using the forces, just using the distances, right? It's going to be the ratio of the input distance divided by the output distance, right? Does that make sense? So theoretically, it should be 2, right? So it should be, you know, this is really the way that we would calculate ideally what it would be. In actuality, the forces may not play out that way. There may be some other forces going on that mess us up, right? But this is going to be, instead of calling this L and Y, let's call it this. Let's call it input distance over output distance, right? Because what we're trading here, the amount of extra, the ratio of the extra distance that we're having to apply to the machine divided by the distance that's actually being accomplished, in this case vertically, how far did we lift the thing? That's predicting, theoretically, what that machine's mechanical advantage is going to be. Does that make sense? Right? So theoretically, we're thinking we're going to get twice the benefit out of this. In reality, we didn't. We only got 1.5 times the benefit. Still might be worth it though, right? In fact, what if we even had to apply, what if it was really a very sticky ramp, right? Lots of friction, and we had to apply the same amount of input that we normally would. It still might be to our advantage to use the ramp. How come?
Because you may not actually be able to lift it up.
Because we may not be able to lift it up, but we might be able to apply the force in that direction, right? Maybe we're going to hoist it up with a crank or something, okay? So there are other advantages to a simple machine. They do 2 things, potentially, these simple machines. We'll look at some other ones, too. For today, we just took a ramp. But there's really 2 things they do. They can multiply the force. Maybe we want to do the opposite, multiply the distance, and we'll talk about that later. But they have the potential to multiply the force, but they also change the direction, right? So changing the direction sometimes sometimes that's a game changer. Sometimes that's all we need is just to change the direction, right? Okay, so try one for me.
Is that what it is?
Let's say we've got a ramp. Here's my ramp. and let's say that the length of the ramp is 12 meters and the height of the ramp is 3 meters. Okay, I want you to calculate what's the theoretical mechanical advantage of that ramp. So theoretically, how many times are we multiplying our input force? Anybody agree? 4? Because we got input distance over output distance is 12 meters over 3 meters, the units cancel, and we get 4. Okay? So let's say that the load is 500 newtons, and the input force, the actual measured input force, is 300, let's say. Okay, what is the actual mechanical advantage then? What did we say that was? The actual mechanical advantage is really how much the force is multiplied. So it's the ratio of what divided by what?
Input force.
But which one's going to go on top?
The
3 and
five.
Output on top, good, over input on the bottom, right? Okay, and that's going to give us, what was it, 500 newtons over 300 newtons. So 500 over 300 is 5/3, what is that? 1.67. So we wanted 4, we thought we could get 4, but because of the friction on the ramp, we only got 1.67. Okay, last issue for the day. What do you suppose we could call the efficiency of this machine?
the
1.67 divided by 4.
Or the other way around. What do you think the efficiency is?
the
40%.
Yeah, the theoretical divided by the actual output.
Other way around.
Actually divided by.
So one way to calculate it, we'll talk about another way tomorrow, but one way to calculate efficiency is the actual divided by the theoretical.
And it'll only, and it can't get.
What do you suppose the highest efficiency could ever be is? Yeah, 100% or 1.
I'm thinking, because it's impossible to get more energy out of it.
Yeah, that would be a good, if you, I tell you, if you invent that one, I'll go into business with you, okay?
Smart.